perturbation theory could be there, lambda to whatever power. But what about the dimensional thing? You could have let me do one thing. Symmetry. Symmetry is a great gift in restricting the effective action. As I told you, the effective action is symmetric unless the theory has got an anomaly, which is to say it's symmetric unless it isn't, but it often is. Okay? So, for example, one thing is Lorentz invariant. I am not going to write I'm not going to write a counter term. In fact, not only Lorentz invariant, Poincare invariant. I am not going to write down a counter term where the derivative indices, the vector indices here, the space-time indices of fermions or scalars or derivatives are not hooked up to form Lorentz invariants with a T. I'm not going to make the coefficients of this local operator x-dependent because that would violate translation symmetry. So they are x-independent coefficients of Lorentz invariance. So that's an obvious one. But in the case of phi to the fourth field theory, we can insist on this symmetry. Okay? So if I start with an action which has this symmetry, I'm not, in fact, I can show you an explicit regulator like Taulier-Villars or something similar, which respects this symmetry. There's no problem, there's no conflict with having a regulated measure for the path integral and having this symmetry. So this is a good symmetry. Now this will restrict us, okay, to the following possibilities. You must have at least some power of phi, so you can have two powers of phi, and you can have no derivatives. And guess what? We see a term like that there. You can have two powers of phi and two derivatives, by which I really mean d mu phi, d mu phi. It couldn't have been anything else. You see, I have to write something Lorentz invariant to hook up these two derivatives. That's why I can't have one derivative, because one derivative would have an index that I can't hook up to make a Lorentz invariant. So I have to have two derivatives hooked up. The two derivatives could act on the same field, but by integration by parts, I can make it look like this. Okay, so I can't do anything more general than this. You can write phi, down version phi, or you can write d mu phi. They are the result of integration by parts on each other. Okay. I can't have more derivatives because then I will have violated this bound. Okay, because I can't compensate. I don't have negative scale dimension things in this product. They're all positive. Okay. Once this is already equal to 4, that's as far as I can go. I can have more phi's. I can have phi to the fourth. That's also even under phi goes minus phi. But I can't afford any more derivatives according to this rule. And that's it. That's all I can do.
Well,
so this derivative to the 0th power is otherwise known as this. But, yeah.
so this is a little bit perverse, but could you have phi squared m and then something? Seems
yes. So what about the coefficients of these? Okay. See, for me, it's not important to what I'm talking about right now, what the coefficient is. I just use that dimensional analysis to restrict the set of local operators.
Okay.
But indeed, if we talk about what the coefficients could be, they could be things like m squared, phi squared, they could be m squared, log lambda, phi squared, they could be lambda squared, phi squared. All of these are consistent with the basic things I was pointing out there. This thing, d mu phi, there's no room for power of the cutoff. still get a log lambda, d mu phi, d mu phi. Same with phi to the fourth. You couldn't get lambda squared phi to the fourth. There's no room for it. But you could get log lambda. You could even get log lambda over m phi to the fourth, things like that. Okay? But the main thing is the set of things I have already told you about, just hoping that familiarity would lead to acceptance, was in fact the full list. Okay? We didn't need any other, it couldn't have come about any other count. Now I remember. I said this, but I just want to, now that I've written this out, I will say it again to emphasize. The locality of this L diversion, the divergences, depends on having already at order h bar to the n plus 1 depends on having already introduced counter terms to remove divergences in subgraphs. To order h bar to the n. You can read a little bit more about it in testing, but basically, this is not got very much content in one loop, but at the multi-loop level, you're doing 2 loops or 3 loops. I claimed that the sort of basic insight that divergences are local even at higher loop level, beyond what I actually proved, is true. But only if all subgraphs have already been rendered finite by introducing counterterms in lower orders. Then the n plus first order will introduce a new set of divergences, and they will be local. If you didn't already renormalize, if you just sort of said, look, I'm just going to do a 10-loop graph without having worried about divergences at all. If you just start looking at that, you will start to see divergences that don't look like they are local. And that's because nested inside these graphs are subgraphs which have local divergences, and the local divergences are multiplied by finite non-local pieces of the entire graph. So I'm not trying to emphasize this in this level of the course, but if you read a little bit there about going beyond one loop. In fact, if you just play by the rules of renormalizing order by order in perturbation theory, you are not going to hit this issue, because it will take care of itself because of this statement. But, so, a small aside, but an important aside for saying that this theorem that divergences are local is true is to be read in this sense, yeah.
So for these log lambda over m terms, we need the over m for dimensional reasons. But how does that...
No, not necessarily, sorry. You might not have the n. So this was an example, sorry. Here, let me write that, okay, and write as a separate possibility things like log m phi to the fourth. Why am I making that, why am I saying no here? Because one thing you could have had is you could have had some Green's function containing something that looks like log lambda over some energy when you Fourier transform gamma from x space to p space. You could have got some p, and that could sit in the denominator. Now, the log of e piece of this since it's not polynomial, is it is not local. It's not local. But the log lambda part, since it is polynomial in momentum, in fact it's independent of momentum, it is local. But the two are entangled in this way. So I can write this, often to make this absolutely clear, we can write this as log lambda over your favorite mass scale, choose one out of the hat, plus log mu over E. So this is something finite but non-local. This is something local but not finite. But neither of them includes M, which was your question.
Okay. And what prompted me to ask the question was just the fact that the fact that M should only come polynomially, and that you talked about, that doesn't prevent log M terms or anything.
Sorry, it does. My God. Yes. Yes. This is out. This is out.
Okay.
Good. This can happen. This can happen. The log M cannot happen. The log M can actually happen, but only in a finite way. And in fact, there's nothing wrong with my saying this can happen. In fact, it does happen. Okay? There's nothing wrong with my writing that, except that it violates what you heard me say was the theorem. So you say, well, how can it happen? Well, notice that what I've written here is actually finite. This is finite. So the reason I'm scratching it out quickly is because it doesn't belong in the list of divergences. You can always introduce it in some scheme where you're adding some finite thing just for the heck of it, or because your scheme says to do it, or there's some other logic, or it's easier to compare data to the scheme. But it is not strictly divergent, and the theorem is applying to divergences. But indeed, it's sort of you could write it in the list. But I'd rather you not think that way, because I don't want you to think that I was lying when I said that things are polynomial in M, if they are divergent. Okay. So let's see. Okay. I think I was going to do the general case of this to try and understand, in the big scheme of things, all things that can happen in any theory. So what are the set of theories, and how do they play according to the set of divergences? But I wanted to get onto a practical calculation, so I'm going to defer that. Yes, I will defer that. Now, what did I want to say though? So anyway, here it implies that indeed S bare, S renormalized, and S counter term all of the same form. Okay, they're all made out of just these three operators. And so the way I discussed everything indeed follows the way I wrote it out, but you might have had the loophole question, why is he always restricting himself to these? Does he really mean that there's something else, but he's not bothering to write it down? Well, this is the logic for why it saturates exactly at this point. Now, what did I want to do? The time is going to get me. Let's see. I will try and reorganize. Let's say it so that. Yes. Let me be brave and move things around so that I can try and squeeze it into the center. practical calculation and introduce the most practical of the ultraviolet cutoffs. I'll never finish. But I try. Let me try and do something, because we've had the air of abstraction for too long. So, an example is one loop, 5 to the 4th, so-called fish diagram, thought of as a contribution to gamma, okay, in the 1 pi sense. So this gamma, one loop, that's the order at which I'm working when I'm writing this thing, phi. It contains, so what do we mean when we draw this notation around it? Well, there's an integral before x, and integral before y. If you want, think in position space where that's x and that's y. You see, because both of these lines, in this particular diagram, both these lines are coming out of the same space-time point y, and these two out of the same space-time point x. So I don't need 4 integrals, I only need 2 integrals with 2 phi's each. Okay, that's this one. And then there's the usual minus I lambda squared, coupling constant. And in fact, we know what the actual diagram, the sort of the guts of this is. In position space, it's very easy to write down. It's just a propagator from x to y and multiplied by another propagator from x to y. And that's it. Except, and I was going to do this carefully, I'll do it carefully next time, exactly which number should I put? How do those combinatorics work again? Now, I'm used to doing combinatorics for connected diagrams, but this is not connected diagrams. These are one-particle reducible diagrams. Do they have the same combinatoric vector? Let's do it next time. Okay. So there's some number there. Maybe I should even tell you what it is. It's 16. Okay. But justified. Next time. And I can, however, just conceptually, I think, in position space, but I calculate in momentum space like everybody else. So this is equal to 1/8 integral d4p1 down to integral d4p4 if you want, but secretly with a delta function, p1 plus p2 plus p3 plus p4. Everybody's incoming momentum. And then there's phi of p1 down to phi of p4. So that's easy. And then there's the minus I lambda squared factor again. Well, let me separate that out. Okay. And then multiplied by minus I lambda squared over 2, which is the naive symmetry factor. Okay, so the fact that it was 16 requires some discussion, because if I were just thinking of this some random thing, I would say, oh, look, there's that factor of 2 symmetry, I would put it there. So this is, if I were connected diagrams thinking guy, I would write that. 2. This needs to be justified. But let's not worry about factors. It's boring. For the moment, till next time. Integral d4, the loop momentum. Then there's a propagator. And then there's another propagator. And you do that loop, and that is secretly just doing the Fourier transform back to this incredibly simple expression here. But in momentum space, this is what it looks like. And this part of the expression here, I just want to go to the Feynman parameterization. That's easy to do. This looks an awful lot like the self-energy kind of loop. Not exactly, it's not the same, but it looks very similar. Again, there are two propagators multiplied. You want to sort of get just sort of, you want to disentangle this so that it's just, it looks like a kind of single propagator to a power. That's what the Feynman parameterization does. And what else do we want to do? And after that, we learned in one of the homeworks that we can Wick rotate the Q, at least, can be Wick rotated, the loop interval. And so what do we get? We get lambda squared over 2 integral over the Feynman parameterization, and then integral over this Euclidean momentum Q. And here it's this Q squared, Euclidean Q squared plus M squared. Times 1 minus x, and then plus this P plus Q squared x plus M squared x. Where this P is obviously the P1 plus P2. Just remember, or go back and look at the self-energy calculation, and you'll see how we are following it in very, very closely. And this is equal to lambda squared over 2, integral x, integral Q, and we can tidy up this to look like Q squared plus M squared plus 2P dot QX plus P squared X. This looks so much like one of the terms in the self-energy case that we're not going to keep writing the I epsilon and so on. So it's important. I epsilon has got a role to play, but you put it in, it's M squared minus I epsilon. But let me not keep writing that up. Just move faster. You know where the I epsilon goes. And it's all squared because of this Feynman trick that we're playing. Okay, so I'm going to run out of time. What do I want to say? I want to say, well, let me introduce this idea of the regulator first. This integral is around the hairy edge of being convergent, but it's still not convergent. It goes like integral d4q over q to the fourth, so we know it's logarithmically different. One thing, so we are about to attack this with a regulator known as dimensional regularization. And the idea is to note that if only we had lived in fewer dimensions, this would actually be a convergent integral. Like if I lived in 3 dimensions, then I'd have 3 powers of momentum up the top and still have the same old 4 dimensions, 4 powers of momentum down the bottom, and this would be an ultraviolet convergent expression. Life would be good, but unfortunately we don't live in 3 dimensions. Okay. The idea is to imagine that you lived in fewer dimensions, and to, in fact, I'll have to slow down and say this again, but the idea is to say that you keep the number of dimensions d that we are considering doing quantum field theory in, you're keeping it floating. And the main thing that happens in at least perturbative Feynman diagrams, and I don't know any sense that it is true outside of perturbative Feynman diagrams, but in perturbative Feynman diagrams, not only do you have sort of analytic functions of momentum and masses and so on, They're also analytic functions of, analytic with some singularities thrown in, but they're analytic functions of this D. And we're going to, I'm asserting that, we're going to just check this case. But because they're analytic functions of D, you can do something that is often done with mathematical functions. There's a way of describing how you came, you sometimes come to a math function through some physics problem or another that you're trying to solve, and you have some representation for a function. And you say it's clearly this function is well defined in this domain, this range of its argument. But outside that range, it's not defined. But we have this time-honored way of dealing with that, which is called analytic continuation. We can define the function in a restricted domain through some very explicit way of writing it, and we can define it outside that domain by trying to analytically continue. Okay? Here, if this had been 3, this would actually be a convergent interval. If I called it D, and D is somewhere in the vicinity of 3, say, even though we know from the physics point of view that there's no such thing as a fractional dimension, as a function of D, this path integral, as I will show next time, not path integral, this Feynman integral, as a function of D is actually well defined. Mathematically, you could talk about what this integral is as a function of continuous D. And we'll see how to do that. And in the vicinity of D equals 3, it is convergent. And in the vicinity of 4, we see that it is starting to be not convergent, but we can try to define it by analytic continuation. So maybe the quickest thing I can say is say, look, that just sounds insane, but remember the classic example. N factorial is equal to n times n minus 1, down to 1. This is so obviously defined as a function of an integer that it is insane to think that you could define this for n fractional. And yet, there's that beautiful generalization of this. The gamma function of n plus 1. For n integer, it is exactly this, but it interpolates beautifully in between. Okay? So, this is defined in that sense for fractional n. On the other hand, gamma of, say, negative n, by the usual, well, I'll show you in the next, these are actually related. So we'll see that gamma n can be, you can define an integral, you can define this to be the result of doing an integral, which for integer n would normally have just given you n factorial, but now it defines some other function, which is this gamma function. Even the gamma function defined by an integral representation doesn't make sense for, say, negative n. But we can define it using analytic continuation. And this is sort of very similar to the trick that we're about to pull here. Here, too, this seems to only make sense for integer d, but the structure of these Feynman diagrams will make it very natural to define Feynman diagrams in fractional number of dimensions. And then we will see that when we think of it as a continuous, in fact, even a complex variable, the number of dimensions as a continuous and complex variable, that we can even define these integrals where they would naively be divergent by analytic continuation. Now, somewhere there, you should not lose sight of all that matters, which is, in the end, we are trying to, any regulator, any ultraviolet regulator is okay. We don't really believe that there's Pauli-Villars particles out there. We don't really believe, well, some of us do, some of us don't, that there's a space-time lattice at very short distances. And we don't really believe that the number of dimensions is continuous. All that matters is that this kind of meddling with the integral that physics hands you is only doing violence to the far ultraviolet. If it is not doing any violence to experimental energies, then it is merely a regulator, merely an intermediate step, which we employ for convenience. The reason that we do this is the most abstract of the regulators that we have. But the only reason for using it is because calculationally it's the simplest. So there's a price to pay for its technical simplicity, which is its abstraction at first sight. So next time I'd like to introduce it again. I'd like to point out that it's not doing violence to the infrared. It's only a way of cutting off the highly virtual momenta that are causing divergences. And so any regulator would do. This is just one, not to be taken too seriously, except it is deadly seriously the way to calculate in practical